and the quasiparticles live longer and longer as soon as you consider them closer and closer to the Fermi surface. If you take them far away from the Fermi surface, then they start to decay. Let's understand where this psi p square comes from. And this is again very simple. Since 1 power of psi is just energy of quasiparticles, and this is a relative number of quasiparticles accessible to the interaction, for the interaction. So this is how decay of quasiparticle occurs. Of course, you may say that the reason that you have this interaction and so on is the temperature. As I said, temperature produces your excitations. So temperature is sufficient to remove electrons from inner side of Fermi surface and put it outside. It smears out step function, and therefore you can say that if we assume that the energy of excitations of the order of temperature, then 1 over tau, or rate of the damping of quasiparticles, is something like t squared over Fermi energy. So this is actually a very important statement. This is the essence of Fermi liquid theory, that first of all, quasiparticles are well defined as soon as they live very close to Fermi surface, and then the decay rate appearing due to interaction between quasiparticles is proportional to second power of energy, which can be temperature, magnetic field, frequency, whatever, divided by Fermi energy. Okay. The last thing which I would like to say in summary is what happens with the Fermi distribution function when the interaction is taken into account at 0 temperature. So this was distribution function, and energy is a function of energy and a Fermi energy for ideal Fermi gas, non-interacting system. The theorem which I formulated for you, Landau theorem, says that the Fermi energy is still connected with the total density of particles and doesn't change with interaction. Therefore, this energy is the same. However, the mass is different and there is a damping rate. So, if we now plot the interaction function, it will take this form where there is a jump at the Fermi surface. This jump, z, is of course smaller than 1. And it characterizes the interaction too. So now I'm saying that interaction is not only encoded in the mass of quasiparticles, but also manifests itself in the jump of the distribution function, and this is t equal to 0. Don't confuse it with the final temperature smearing out of the distribution function. So this is how Fermi liquid looks like. You may ask me other examples where we don't have Fermi liquid. Well, there are. And the topic of what is Fermi liquid and what is not Fermi liquid was very seriously debated when the high temperature superconductivity was discovered. Namely, I hope Professor Yevtushenko can tell you a little bit about high temperature superconductivity, this modern and very hot topic. No explanation of mechanism of this superconductivity is yet found. It was discovered in 1986, got a Nobel Prize a few years later. Recognition comes in practically immediately, but the structure of these materials is quasi-two-dimensional. So these materials are kind of ceramics, the substances which people believe are rather insulated than good metals, and then being chemically doped by impurities, system eventually become superconductor with the high temperatures, higher compared to helium temperatures, nitrogen temperatures, which is a big technological advance. Would it be good metal, then one can make a wire, and since liquid nitrogen costs many times cheaper than liquid helium, one can produce superconducting magnets and so on and so forth. But as I said, unfortunately, these materials are ceramics that are not good technologically for production of wires, but they are quasi-two-dimensional. And the question was, if there is breaking down of Fermi liquid concept in two-dimensional system. And after long debate, the answer was no. In two-dimensional metal, you still have very good metal described by this theory. Namely, you have a connection between Fermi momentum and density of particles, and you have jump in your distribution function at this energy. What about quasi-one-dimensional systems? What are the quasi-one-dimensional systems? One of the examples one can have in mind is organic materials. Some moleculars, long moleculars, which conduct in one dimension preferable direction and do not conduct in any other direction. Another example is carbon nanotubes. The materials which were fabricated, it's tube made of sheet of graphite, rolled it out, and then these tubes can be much longer compared to their diameter. So typical diameters is few tenths of angstroms, and typical lengths are kind of micron. And this is another quasi-one-dimensional conductors which can conduct electron current. And it appears, and we, I hope, touch a little bit this many body effects, that in one dimension, Fermi liquid concept doesn't work at all. And what is wrong with one dimensions is precisely this one, that fermionic quasiparticles are not well defined just because their damping rate is always comparable with their energy. So if damping is of the same order as energy, one cannot say that these entities, quasiparticles, are good for interpretation of a description of system. However, in one-dimensional system, there is much nicer way to proceed with the calculations, which is known as a bosonization. So it appears that true excitations in the system are bosonic. They describe the properties of this system, and this is how properties can be studied and calculated. But, of course, at the end of the day, one can come back to calculation of some fermionic correlation function, but the true and natural language for one-dimensional systems is bosonic. So, although I start telling you this Fermi liquid concept and so on, saying that I'm in three-dimensional case, two-dimensional case is still okay, but not one. Okay, good. Any questions related to this?
Sorry, I didn't understand this energy jump. What is this jump?
It's not jump, it's a jump on the Fermi momentum. This jump, which was for ideal gas, was also there. So it was a step function. And this jump was precisely 1. So now we have some similarity with the step function. So jump also occurs on the Fermi energy, but this jump, due to interaction, is smaller than this one. Therefore, it's smaller than 1. But it still exists. It's very important. The reason why it is smaller than 1 is due to interaction.
So it means even at zero temperature there will be some empty states below.
Of course, interaction removes you. Yeah, interaction creates holes, of course. Okay. But alternative could be that there is no jump whatsoever, and behavior is of that sort. So it's a power law singularity. And this alternative is realized in one-dimensional systems. So, and this is the reason why the excitations are badly defined. You see, in my calculations, I use the zero temperature. I put all functions as step functions, and this is why I obtain this result. Would I not have a jump, would I not encode this jump at the very beginning, I would get just power, just due to absence of the jump. And then, from here, I will see that the energy and the decay rate are the same, up to some numerical value. Okay, in remaining 20 minutes, what I plan to do is to study properties of the Fermi distribution function, some useful properties which we will need for our future action, regardless whether we decide to refresh our derivation of the specific heat or not. Okay. We have n epsilon equal to 1 over e to the power epsilon minus mu over temperature plus 1. For simplicity, I am back to ideal Fermi gas. Let's study derivatives of the Fermi distribution function with respect to temperature and energy, and see how can one calculate integrals which involve Fermi distribution function and its derivatives. This is the goal. So first of all, dn over d energy is equal to minus 1 over e to the power epsilon minus mu over temperature plus 1 square e to the power epsilon minus mu over temperature, and here times 1 over temperature. Correct? So let me work a little bit. This is minus 1 over temperature, and here I subtract from denominator the same power of this. So what I have is e to the power epsilon minus mu over 2 temperatures plus e to the power minus epsilon minus mu over 2 temperatures square. Since I subtract, I have e to the power epsilon minus mu over 2 temperatures square e to the power epsilon minus mu over temperature. And I did it in order to cancel this out. So what I see in the denominator is part of hyperbolic cosine, right? So this is minus 1 over 4 temperature, 1 over cosine hyperbolic square, epsilon minus mu over 2 times temperature. This is a derivative. I'm pretty sure that Professor Müller said you something about that, but maybe said it in a different way. If we plot now minus derivative of Fermi distribution function over energy on the same plot, what shall we see? This function is very narrow picked for the energies in the vicinity of chemical potential, because it behaves exponentially. So it decays exponentially if the argument is large. So therefore, this minus derivative is nearly delta functional. Okay? And then, when I will calculate integrals with this function, I will take into account that the derivative behaves in a way very similar to delta function. Let's calculate derivative dn with respect to temperature, which we, for example, need when we study thermodynamical properties of ideal Fermi gas. Once again, we take this function, it is minus 1 over e to the power epsilon minus mu over temperature plus 1 square e to the power epsilon minus mu over temperature here. So what we will have here, it's minus epsilon minus mu over temperature square. This is what happens when we differentiate the argument, assuming that chemical potential doesn't depend on temperature, but there is also minus 1 over t d mu over d temperature. As I said, chemical potential, as any thermodynamic potential, depends on its arguments. So, if I collect terms, I have plus 1 over temperature, e to the power epsilon mu over temperature, e to the power epsilon minus mu over temperature plus 1 square, and here I have epsilon minus mu over temperature plus d mu over d. What I see here is, of course, this one, yeah, this part up to sign minus. Therefore, I have very nice expression that dn over d temperature is equal to minus dn over d energy times epsilon minus mu over temperature plus d over d. Very nice equation. And this equation actually is used if we calculate the specific heat. Is it clear? It's very simple. Let's now introduce another quantity which we need, namely density of states. What it is density of states? Suppose you need to calculate integral over dp to pi q some function f e. You can write it the way you add some integral over d energy dp delta epsilon minus epsilon p. F, we suppose it depends on energy of epsilon p. It doesn't depend on p directly, but depends on p through the energy. And then we write F energy. So what I did, I add integral with delta function, which is 1, and then replaced the argument epsilon p to epsilon. So I have epsilon p sitting here. So I define this quantity, namely I define the quantity mu, which depends on epsilon. I put 2, taking into account summation of a spin, dp over 2 pi q delta epsilon minus epsilon. And I will call this quantity density of states. This is density of states. It characterized how many states you have at given in the interval from epsilon to epsilon plus d. Let's calculate the density of states for two examples, namely free electron gas in 3 dimensions and free electron gas in 2 dimensions. The notation of density of states is extremely useful. We will use it in practically all lectures, and therefore I would like to spend some minutes for deriving it. So, 3D case. Epsilon p is equal to p squared over 2m as usual. So, mu epsilon is equal to 2 times integral p squared dt over 8 pi cube 4 pi is solid angle. Here you have delta epsilon minus p squared over 2m. Therefore, I will write it as 1 over pi squared. I will multiply it by m and divide it by m, so it's p d p squared over 2m delta epsilon minus p squared over 2m. Of course, you may ask me about limits from 0 to infinity. From 0 to infinity. You understand how I wrote this. dp squared over 2m is equal to p dp over m. M cancels here, and p times p dp is p squared dp. So then I take the integral, introducing the new variable. So then it's equal to m. P is equal to square root over 2m epsilon over pi squared. So the density of states behaves in 3-dimensional case as a square root, but of course we will always be interested in Fermi energy, very large values. So in the vicinity of Fermi energy, remember that I taught you that the states in the vicinity of Fermi energy are important, and these are the only states are important. So if epsilon is equal to epsilon f, this is mpf over pi squared. So this is the density of states at the Fermi energy. It is constant. And as I said, we will be always, well, square root, of course, should have infinite derivative. We will be always interested in this small area, so we can always adopt the approximation that the density of states in the vicinity of Fermi energy is a constant. Let's do the same for 2-dimensional case. As exercise, mu epsilon is equal to 2 times integral from 0 to infinity p dp over 4 pi squared and 2 pi is angle delta epsilon minus p squared over 2m. So it's equal to 1 over pi, and I will multiply over m and divide by m integral from 0 to infinity d p squared over 2m delta epsilon minus p squared over 2m. So it is equal just m over pi. In 2-dimensional case, density of states is a constant, regardless whether I'm on Fermi energy or not. So what was approximation in 3-dimensional case will be exact in that sense in 2-dimensional case. Good. And the last step which I would like to do is to ask if we have integral over energy f energy times nu times dn over d epsilon of that sort. What this integral is equal to. You have seen that dn over d epsilon is a function which is narrowly peaked in the vicinity of chemical potential. Therefore, what we have to do is to expand our function f in Taylor series in the vicinity of the chemical potential, and then calculate momentums of this function. Namely, if we write that f epsilon is equal to f mu plus f prime mu epsilon minus mu plus 1/2 f double prime mu epsilon minus mu square plus and so on and so forth, we can implement the fact that the derivative of the Fermi distribution function is almost delta function. First of all, we observe that this derivative, and I recall you that dn over d epsilon was equal to minus 1 over 4 t 1 over cosh square epsilon minus mu over 2t. So it's odd. It's even function of epsilon minus mu. And since the integration is taken from minus infinity to infinity, therefore all odd momentums should be dropped. Because you multiply odd function and even function, and their product is odd, and therefore the integration of an odd function of a symmetric interval is equal to 0. Then what we have is to calculate the integral of the sort of dn over d energy from minus infinity to infinity d energy. This is minus 1 over 4t integral over d epsilon. Here it's a cosh square epsilon minus mu over 2t from minus infinity to infinity. This integral can be calculated. First I need to shift variable by mu, then I make a dimensionless variable, and this integral is equal to minus 1. The second integral which I need is integral from minus infinity to infinity epsilon minus mu square dn over the energy, and again I plug in this cosh square. I can calculate this integral, and this is minus pi square t square over 3. As a result, we have that it is equal to f at chemical potential minus pi square t square over 6 f double prime at chemical potential. Plus and so on and so forth if we are interested in higher corrections. But second derivative of the function with respect to chemical potential will give us square of Fermi energy in denominator. So you see that usually these integrals or corrections, temperature corrections to the given observables are proportional to temperature over Fermi energy squared. And this is again essence of Fermi liquid theory, that small corrections are in fact small and quadratic with respect to the ratio of temperature and Fermi energy, which is having in mind the fact that even at room temperatures, temperature to the Fermi energy is 10 to the minus 3 or 10 to the minus 2. The square of this factor is 10 to the minus 6 or 10 to the minus 4. So the temperature corrections due to temperature dependence of Fermi distribution function are small. Okay, I'm done for today. Any questions? So if not, we meet Friday, depending on you. If you tell me at 9:30, then 9:30. If not, I'm coming at 9 o'clock. Would all know where to see the recordings, right? This is ictp.tv. This is Science Dissemination Unit. How did you derive specific heat? You use Sommerfeld formula, taking into account derivative of chemical potential. So there is a better way one can use proper variables and small addition theory, and then it's done in 1 minute. If you're familiar with green function, look what happens the green function epsilon minus psi p minus sigma, and this self energy describes you that this is model dependent epsilon and it has a real part in the negative. Let's write this one as 1 epsilon minus psi p. Now I will write derivative minus d sigma over d epsilon times epsilon. The constant is incorporated to epsilon. There is no constant. Minus d sigma over dp times p. I collect these two terms for the moment. It's 1 epsilon 1 minus d sigma over d epsilon minus, it would be this vf p minus ef, and here it stands 1 plus d sigma over d epsilon. Now I subtract, I will write it 1 over, because I want to put it to the shape of non-interacting particles. F1 minus 1 minus d sigma over d epsilon, and here it's epsilon minus vf 1 plus d sigma over d epsilon p 1 minus d sigma over d epsilon times p minus p. So this df over mass times pf over mass times 1 plus d sigma over d epsilon 1 minus d sigma over d epsilon, I will call pf over m star. So then m star is equal to m bar, which is just basic stuff of Fermi liquid theory, 1 minus d sigma over d epsilon, 1 plus d sigma over d epsilon p, taking the mass shell. So this is 1. And then this z is 1 minus d sigma over d epsilon on the mass shell. Then you are saying what's the condition that this jump is easy to be? That's actually what happens if, for example, sigma is something like epsilon log epsilon. What will be then? D sigma over d epsilon is log epsilon minus plus 1.
So this guy will then behaves as 1 over log epsilon, and this goes to 0. And this is what is people calling marginal Fermi. What I said you that to be precise, this is imaginary part.
And physically, when does it appears? When it's strong interaction?
Yes. Well, not only there should be some topology involved. So in 3 and 2 dimension, non-Fermi liquid doesn't appear due to strong interaction. In 1 dimension, it will. But there are some specific models, like Kondo models, where this kind of self-energy part, well, it's not due to interaction between electrons in the Fermi liquid. One needs to add something extra. For example, impurities or whatever, which make system non-Fermi liquid. Within just electron interaction in 3 and 2 dimension, no way.
Due to impurity. Scattering of the impurity or something.
One example is spin impurity, Kondo impurity. But in principle, good question. What Fermi liquid is, everybody knows. It's well defined.
Definition of the Fermi liquid is that interaction.
But non-Fermi liquid is badly defined quantity. It's model dependent. For some models, one can prove that this Z factor, for example, is 0. Then one speaks about non-Fermi liquid. But one-dimensional case is very specific. In one-dimensional case, as I said, there is no jump. Also because there is a log in this decay rate, one can investigate it and show it, and therefore the n as a function of p behaves as p minus pf to some power alpha, depending on interaction in the vicinity. So there is no jump. And then it says that decay rate of the same order of magnitude as energy. Fermionic excitations are badly defined, and Fermi liquid theory doesn't work. This is why in one-dimensional system people call it Lagrangian liquid.
As a quasiparticle, it's called because of difference of some bases.
It's excitation. As I said, quasiparticle and excitations are synonymous. So we started with a Hamiltonian which describes interacting particles. At the end of the day, we come to the Hamiltonian which describes non-interacting something. And we call this something as quasiparticles. Because we removed all effects of interaction from our initial picture and encoded it in the parameters of the ideal Fermi gas, so to say. Of course, these quasiparticles also talk to each other because the wave package decays. But this is not this initial interacting picture where particles scatters like crazy.